Hello, 8th grade math students. Mr. Lawrence here, and this will probably be the last day for this finding the nth term stuff for you, at least for a little while. But we're going to explore a new type of pattern today, and I'm not going to tell you what it is ahead of time. Let's go down and see what's happening. So here's our first sequence of numbers. I put them in a table already, and I'm going to find the first differences. And notice I have plus 2 and plus 4, and then plus 8, and then plus 16. So they're not matching. So you might think, well, let's go find our second differences. And I get plus 2, plus 4, plus 8. That's not helping me. Notice how it's actually repeating the same pattern. You see that? I only have 5 pieces of information here, 5 members of the set. But if I kept it going, this 2, 4, 8, 16, 32, 64, 128, 256, 512, they'd be doubling all the way. And then as I go down to the second differences, they're doing the same thing. 2, 4, 8, and if I had more information, I could say there'd be 16, and then 32, and 64, etc. And no matter how far down I go, that's just going to continue to happen. That pattern is just going to continue. It's never going to, what the heck is that? It's never going to stop. So instead of pursuing that, I'm going to notice that, oops, I didn't mean to erase that large, hold on a second, that they're all doubling, aren't they? Yeah, the differences are doubling. You see that? To turn 2 into 4, I can multiply by 2. To turn 4 into 8, I can multiply by 2. To turn 8 into 16, I can multiply by 2. When the differences are all doubling, this is called an exponential pattern. Exponential. And it's a little bit different. You see, in this one, the variable, the nth term, is going to look something like this. It's going to go 2 to the power of n. And so when I do my comparison line, when I substitute 1, 2, 3, 4, and 5 in, I'm going to raise 2 to those powers. For example, this is going to be 2 to the first. This one's going to be 2 to the second. This one's going to be 2 to the third. And then, of course, 2 to the fourth and 2 to the fifth. So 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. If you say 6, you will push floor. 2 to the fourth is 16. And 2 to the fifth is 32. How did I get that? 2 times 2 times 2 times 2 times 2 is 32. Well, how do I turn the green ones into the black ones? Well, let's see here. Looks like I'm going to have to add 3. Oh, looks like I'm going to have to add 3 again. And here I'm going to have to add 3. And so this is going to be 2 to the power of n, add 3. So to do this one, the 11th term, I'm going to have to do 2 to the 11th power, which is going to be a very large number. And that's going to be add 3. So let me see here. Let's see, 2 to the 5th, I know 2 to the 5th equals 32. So I'm just going to keep doubling. So I'm going to have 32, 64, 128, and that would be 2 to the 7th, so it's 6, 7. 2 to the 8th would be 256. 2 to the 9th would be 512. I'm just doubling. 2 to the 10th is going to be the double of 512, or 1024. And 2 to the 11th, finally, 2 to the 11th, is going to equal 2048. 2048. Now I have to add 3 to it, so it's going to be 2051. Yeah, this is an exponential pattern, right? Because all the differences are doubling. Let's go ahead and try this one. Let's see here. -8 to -6. Looks like we're adding 2. Then we're adding 4. Uh-oh, it's doing it again. And then we're adding 8. They're doubling, aren't they? And as soon as you realize that they're doubling, then you know you have an exponential pattern. You take the number that is being multiplied, in this case 2, and the 2 is going to be raised to the power of n. And so I'm going to make my comparison list here. And 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16, and 2 to the fifth is 32. And then I say, how do I turn 2 into negative 8? I think I subtract 10. And 4 minus 10 is negative 6. How about 32 minus 10 is 22? It looks like my formula is going to be 2 to the power of n minus 10, right? Now, I just did 2 to the 11th up on the last problem, and I know it's 2048. And so if I subtract 10 from that, I'm going to get 2038. And that's the 11th term in this sequence. Now, will it always be a base of 2 to the power of n? No. Why don't you pause the video and try this one out on your own. See if you can figure it out all on your own. Here comes my solution. Hopefully you've given it a shot. Let's see, it's going plus 6. And then this is going plus 18. And then I think we're going to go plus 54. Yeah, I think that's going to be plus 54. And I just noticed something. They're tripling. Yeah, they're tripling. Look at this. 6 times 3 is 18. 18 times 3 is 54. So this one's going to be 3 to the power of n. And so I'm going to do my comparison line. And so I'll have 3 to the first, 3 to the second, 3 to the third, 3 to the fourth. Whoa, I said 3 and I wrote 2, silly Mr. Lawrence. And finally 3 to the fifth. So 3 to the first is 3, 3 to the second is 9, then 27, 81, 243. Again, how do I turn the green ones into the black ones? Looks like I'm going to add 2. 27 to 29, I'm adding 2. 3 into 5, I'm adding 2. So the formula here is going to be 3 to the power of n. And we're going to add 2. To figure it out, I'm probably going to use a calculator on this one because I don't know 3 to the 11th power. All right, so I'll go to my calculator, and 3 to the 11th power is going to be a very, very large number. 3 to the 11th power is going to be 177,147. Adding 2 will yield an answer of 177,149. And that's the 11th term. I'm not going to rewrite it because I don't think it's going to fit in there. All right, that's it. You've learned how to do linear patterns. You've learned how to do quadratic patterns. And now you've learned how to do exponential patterns. Wow, you guys are really ahead. Great job. All right, so there's a little worksheet with some practice problems for you. And Mr. Lawrence signing off. Have a good day, everybody.